Hey guys, Nick here, and today we're going to take a look at Gauss's law. Now, Gauss's law tends to be one of the more confusing things in physics too, but it also tends to be the thing that you will use the most whenever you're asked about electric fields. So we'll dive right into it, and hopefully by the end of this video you'll be comfortable with how to use Gauss's law to answer questions regarding electric fields. Now, as always, it's really useful to keep in mind through the whole process of learning it what Gauss's law helps us do. Now, the answer is that Gauss's law is going to help us find electric field strengths near not any object, but some restricted class of objects. So specifically, it's only going to be near pretty symmetrical charge setups. So if you have just some general blob of charge and your professor says, find the electric field outside of it, it's not going to work. However, if you have a nice symmetrical object like a uniform sphere of charge, the sphere is very symmetric, Gauss's law is probably going to be the easiest way to find the electric field. Okay, there's bad parts and good parts to Gauss's law. The bad part is the governing equation is ridiculously scary and the notation is just otherworldly. Specifically, this left-hand side is just idiotically difficult to understand at face value. So we're going to rewrite that left side into some more understandable terms. In practice, this left side is never actually used. You always use this simplified version. So don't worry about this. We're going to manipulate that. Second bad part is, as I said up above, it's only useful in these very ideal scenarios where you have a really, really symmetrical object, like a sphere, or a perfect line, or a perfectly thin plate of charge. So you can't use it in general to find electric fields. The good parts are that once we learn the process, you'll find that this equation with the modification to the left-hand side, it's actually pretty simple. Specifically, the math involved, it's at most maybe division. You'll see that there really isn't much math at all, despite the fact that this closed surface integral is a horrifying looking thing. In practice, at most we will be dividing by one number, and that's the end of the problem. And last but not least, these sum scenarios, so these specific symmetric scenarios that you would think only come up sometimes, it turns out they're everywhere. And even if something isn't perfectly symmetrical, you can model it as being very close to one of those, or maybe a sum of these nice shapes. So it'll turn out that you'll be able to use Gauss's law for a huge class of problems. Notable examples will be wires carrying charges in the real world, not necessarily flowing for current yet, but just a wire loaded with charge. You'll be able to use it for a sheet of paper, or really this would be the plate of a capacitor in a circuit if it is holding a charge density. And importantly, you'll also be able to use it for spherical balls of charge. This includes point charges. So we'll actually be able to rederive Coulomb's law using Gauss's law. Okay, now there's some sort of definitions that you don't really need to know when you're doing Gauss's law problems, but it's worth going over them because your professors might ask about them or use the terminology, so I'll go over them rather quickly. The first one is going to be electric flux. And I'm going to say in practice this is relatively useless outside of tests. Until much later in Physics 2. When you do, I forget the name of the equation. It has to do with magnetic fields. It's probably a cardinal sin for me to forget the name of that equation. I just took electrodynamics. But what electric flux is, in short, is it's electric field times area. So just schematically, if you have this may not be a physical piece of paper, it may just be some imaginary sheet, and you're told the sheet has an area of 10 meters squared, and there's an electric field of 5 newtons per coulomb. Let's see, do I have the right units? Yes, I do. And you're told there's a uniform electric field of 5 newtons per coulomb flowing perpendicularly through this surface. All you do is you multiply the electric field times the area to get a total flux of 50 newtons meters squared per coulomb. Again, I use electric flux so little that I don't even know if there's preferred units that combine the meters and the coulombs. But that just goes to show how little you use this in practice. Another note, just because you might see it on a test, if the lines aren't perpendicular to the surface, you're going to have to multiply by the cosine of the angle between, or actually, would it be the sine? Let's see, we can work it out. When the angle is 90 degrees, you get the full strength. So that means it should actually be sine. So flux will equal, I'll explain this equation with an example in a second. So it's the electric field times the size of the area that the thing is going through times the sine of the angle between the electric field and the surface perpendicular. When the lines are perpendicular, that means theta equals 90 degrees, and so sine of theta would then become 1 and drop out of the equation, giving you this one that you actually use in practice, this formula. Okay, next thing is just a quick review of what electric charge density is. You might not have even heard of this yet, and that's okay. So I'll actually go through a little slower than if it were just an example, or than if it were just a review. Electric charge density, it's exactly what it sounds like. It's kind of like how regular density will tell you how much mass there is in an object per unit volume. Electric charge density will tell you how much charge is there per unit volume of an object. Or sometimes, if you're doing in one dimension like a wire, it'll tell you charge per unit length. Okay. And in one specific case that we may cover later in this video, it'll be per unit area. So in equation form, this is written using 3 different symbols depending on whether you're using volume, length, or area. The traditional way to write it is for 3D problems, so those involving volume, the symbol is rho for charge density. And again, this equals the charge of the object divided by the volume of the object. Now, conversely, what we'll usually do is if we're given the rho of an object, all we need to do is multiply both sides by v to get the charge. So the charge would be the density of the object times its volume. And I will actually write this as volume rather than v, so it isn't confused with voltage. Okay, for 2D, this is going to be problems involving surfaces like pieces of paper with charge. We're going to use the symbol sigma. And again, this is going to be charge over area this time. And just like last time, the actual way you usually use this formula is you are given a sigma and you're asked to convert to the amount of enclosed charge, or the amount of charge on the surface. So the rearrangement is the charge is the density times the area, right? This is amount of charge per meter squared, and this is how many meters squared you have. giving you, when you multiply them, the total amount of charge in those however many meters, or however many meters squared. And for the length problems, the symbol is usually lambda, and in this case it's charge per unit length. And again, like before, the actual way you use this is that you multiply the charge per unit length, so like 5 coulombs of charge per each meter squared times 2 meters would give you 10 coulombs of charge in that 2 meter span of a wire. Okay, so I will box these equations, but just understand they're all really getting at the same thing. People have just chosen to use new symbols to avoid confusion in problems where multiple ones might appear. Okay, now let's actually get on to the main meat of this, and it's Gauss's law, which will really use this quite a bit. I'm not sure of the spelling notation if you do another S after. I'm going to leave it like this. Okay, now we're going to do this through a motivating example that we actually already know the answer to. And it's going to be the case of a point charge. So we're just going to have a ball of just a point of charge with charge Q. Maybe let's say you can pretend it's a proton for now. And the question is, what is the electric field at a certain distance away from it? Okay. Now, we already know the answer to this from Coulomb's law because it's a very, very simple ideal case of a perfect point charge. So the answer from Coulomb's law is that the electric field is K times the Q of the charge, creating it, over R squared. And it's in the direction radially outwards. By the way, don't worry too much if you don't understand the R hat, negative R hat notation. I'm going to do a bunch of examples, and you will probably be able to pick up more or less what it's getting at. All these hats are doing is it's telling us which direction the electric field size is pointing in, right? The electric field, in addition to having a size, points somewhere. So the R hat tells us it points radially away or radially outwards. From the source charge. Okay, and again, just from our general knowledge, in the last video I went over this a little bit, of what would happen to positive charges placed near a test charge, we can draw roughly what the electric field looks like. Okay, and this is without knowing the answer. This is a hidden answer that we pretend we don't know for a little bit. Just from the symmetry of the problem, we know that the electric field looks like this. It points radially outwards. It's the same size at a given radius right here. And as you get further away, the field lines get smaller because you're further away from the thing pushing you, and the electric field gets smaller down there. And one more time, this is without knowing the answer. This is just from the symmetry of the problem and imagining what would positive charges do. Okay. Now, once again, Gauss's law's equation is awful. I'm just going to say it equals sad face, because it really is quite sad. You have this awful left-hand side equals the enclosed charge within some surface S over a constant epsilon 0. Okay, now what we're going to do is we're going to phrase this in real world terms that you will actually use. So in real world terms, what you will do is you're going to draw a special surface around the charge you're being asked about. So it can be a charge or a charge setup with multiple charges or lines of charge you're being asked about. Okay, and I'll tell you what the properties of the surface are in a second, but what that is going to do is that will simplify the horrible integral sign into a multiplication of electric field times the area of the surface. Ooh. Hitting my erase button by accident. Okay, and that is a huge simplification. It gets rid of this awful circulation integral, and it replaces it with just a multiplication. Now, again, our setup is there's a charge right here at the center, and we're asked to draw this mysterious specific surface. Some people call it a Gaussian surface, so I'll write that. Okay. The rules for picking the special surface are this. Okay, rule 1 is the electric field should have the same size everywhere on the surface. So size / strength. So, for instance, we know the electric field points radially outwards, and it has the same strength at all radii. And by the way, this is a 3D problem. Oops. Okay. So, if we were to draw a surface like this, so far for our first condition, that's good, because the electric field arrows all have the same strength everywhere on the surface. If we instead were to draw a less correct guess like this, okay, the electric field is weaker out here. So the electric field arrow here is bigger than the one here, which violates this rule for picking the surface. You're trying to pick a surface where the electric field has a constant strength everywhere on it. So this would be a bad guess. Okay, the second condition, and this one is usually automatic, but I will mention it still. The electric field should be perpendicular to the surface. Okay, and I'm going to put the first one in our handy Galaxy pen to remind you that this is supremely, supremely important. That the entire art of these problems is going to be drawing the correct surface. Okay? And so much, I'm actually going to make a remark in Galaxy pen. For each problem, you will need to draw a different surface. So a different shaped surface. Okay, and I'm going to box this and double underline it all in Galaxy pen, because this is where people go wrong in Gauss's law. So I'm going to show you a surface that works for the point charge, but we will have to use a different surface when we're trying to build a surface around a wire, because if you draw a circle around a wire, as we'll see, the electric field won't have the same size everywhere on the surface, and that will be a problem. All right, so let's continue back and let's see if we can draw our Gaussian surface for the point charge. And as I mentioned, 2 is usually automatic based on your drawing, so you don't really need to worry about it. Let's see, if we have all these arrows and we know that they're the same size at a given distance from the center, then easy. We just draw a surface at some radius r. Okay, so I'm going to call this radius r. And that satisfies both conditions. The electric field is the same size everywhere on it, and it also points perpendicular to it at all directions. So perfect. We've got our Gaussian surface. Okay, now what the simplification is that when you pick a Gaussian surface, oops, I haven't left myself enough room. Horrible integral, it goes away and it becomes electric field size at that distance on that surface. Okay, right? Depending on which r we pick, the electric field will have a different size, and that's fine. And we're just going to leave it as a radius for now that we haven't picked, times the area of the surface. And again, it's of the surface at that radius that we haven't really fixed yet. Okay? And at this point, the equation simplifies enormously. Oops. Okay. And this is really the Gauss's law that you use in practice. This reduced one down here on the bottom. E times area, not circle integral E dot dA. It's just E times area, but this all hinges on using a correctly picked surface. Okay? Now, on the right-hand side, I don't know if I mentioned this yet, this is charge enclosed within the surface. Okay, any charge outside doesn't count at all. Okay, and just like these two quantities, it is the charge enclosed within the surface of that radius that we haven't picked yet. So for example, if there are other charges out here, as you increase the radius, Q enclosed will jump as you make R bigger. We'll see how that works in a later example. Don't worry about it too much right now. Okay, so let's apply this to our problem here. I will redraw the picture down here. Oops. Okay, so the electric field on the surface at that radius, that's what we're trying to find. It's still an unknown, so we're just going to leave it as E. Okay, what's the area? So again, that's the surface area of a sphere of radius r. Okay, that's going to be what we'll put in for area. Again, this is a 3D sphere, even though I can't really draw it too well on a piece of paper. Okay, what's the surface area of the sphere of radius r? It's just 4 pi times that general r squared. Okay, perfect. Left-hand side is actually done already. On the right-hand side, what's the enclosed charge as really at any r? I was going to say as a function of radius, but as we grow the circle, we don't catch more charge inside of it. It's just q all the time. So q enclosed is just however much charge was at the center q, and epsilon naught is just some numerical constant. And that's Gauss's law done. We've wrote the equation, and now all there is to do is divide this over. And that will give E. Okay, so we're going to divide both sides by 4 pi r squared. And this is the answer for the size of the electric field at a radius r. And you might be wondering, that isn't Coulomb's law, but actually secretly it is, because 1 over 4 pi epsilon naught, this is what Coulomb's constant K is. They're the same thing. So you may see Coulomb's law written either way. So this does agree with Coulomb's law. Awesome. And now for the direction, remember we got the size, we still need to specify the direction. The direction will come from us looking at the problem and assigning it the direction that it points in. So from the symmetry of the problem, we already noticed / sketched that it points in the radially outwards direction. So if you want to make this a full answer, you could write it like this. Electric field size is kq over r squared. Again, you could write this as 1 over 4 pi epsilon naught if you want. This is the size of the electric field, and if we additionally want to specify the direction, we can put an arrow over the E and write r hat on the right to indicate what direction it points in. And this would be a complete 100% answer on a test. And by the way, guys, this problem does appear on tests to solve this using Gauss's law. The other examples I show will probably appear more often, but you'll see they aren't that much more complicated. All right, so if you hung on more or less through that example, we're going to do another example, see how the situation might change, and after that you'll start to catch on really rapidly. So let's dive into the example of a line of charge. Again, this is not a current carrying wire yet, it's just stationary charges, not flowing charges. Okay, the one complication here is I'm going to tell you what the charge density is. Okay, the charge density is going to be some variable that I call lambda 0. So I'm not going to tell you the total charge like last time, Q. What I'm going to tell you is the charge density rather than total charge. So to get the charge out of this, remember, we're going to have to do something like multiply the density by a length of wire to get the charge within that length. Okay, so step 1 as usual is going to be pick a Gaussian surface. Okay, now remember the condition is that the size of the E field has to be the same at all points. And there's that second condition that doesn't really matter, and it's that E has to be perpendicular at all points as well. Okay, so we have a line of charge. So if we just sketch the electric field, we know it's going to point outwards from the line at each point, right? If we have some sort of like little circle here, it's going to point radially outwards just from like our intuition of what the symmetry looks like. So there's going to be some sort of like a cylinder, I guess. wink wink, where the electric field is all constant. Okay? And automatically condition 2 has been satisfied. And this sort of gives us a hint that maybe we should try drawing a cylinder around the line and seeing if the electric field on it has the right properties for that to be the correct surface to draw. So if we draw a cylinder around here, okay, again, oops, the electric field has the same size on these sort of like circles going around the wire. And that's just from our knowledge of like distance to charge arguments, not because we know the answer already. Okay, so condition 1 and 2 have been satisfied, except on these endpoints. So I really suppose I should put a remark 3 here, and it's that places where the electric field points along the surface sort of get excluded from this rule. So this means parallel, by the way. And usually you'll do this at endpoints of these cylinders and such. Usually at endpoints of your surface. Okay, so for example, on the ends of these cylinders, the electric field is pointing like along the surface radially outwards. So roughly speaking, the electric flux, which remember has that pesky sign of theta factor, is actually 0. So roughly speaking, you don't have to consider the fact that, oh, the surface doesn't have the E field perpendicular everywhere. Places where the electric field is parallel to the surface are allowed, as long as at the rest of your surface where the electric field going through the surface is not 0 is constant. So we are allowed to have these endpoints. So it turns out, so the cylinder is the correct answer. And again, I just want to point out, we drew a different shape for the different charge setup. Okay? For the point charge, we had to use a spherical shell, and for the line, we're going to use a cylindrical shell. So we had to pick a different area depending on the surface, and that's really all the artistry that is in Gauss's law. Okay? So we're going to do a cylinder, and again, we're going to have it at some generic radius r. And now remember that Gauss's law, when we pick this perfect surface, it simplifies immensely. It's just electric field times the area, and again, it's at that undetermined r, equals the enclosed charge over a constant. So all there really is to simplify the area and simplify the enclosed charge, and then we're done. Now, the area of a cylinder, we know it's 2 pi r times the length of the cylinder, but we haven't given the cylinder a length yet, so we're going to have to sort of artificially input a length here. We'll call it L. Okay, so area, I'm going to replace it with, oops, it should be a times. And again, L is sort of, we haven't really picked how long our cylinder is, and it shouldn't really matter because any cylinder is equally as good. And we'll find that L drops out of the answer at the end, which is good. And so really, it's just a calculation / visual tool. That we only use as an intermediate. Just make sure my battery's not about to die. No, we're good. Okay, and the only thing that's left is what is the charge enclosed within this cylinder? And at that point, the problem will be done. Okay, so what is this? Now, remember, I didn't give you the total charge of the line. And by the way, this is a very long line that prevents things such as near endpoints. The field has crazy shapes. This line is taken in the limit of it being really long and really, really ideal. So I didn't give you the charge total on the line. I gave you the charge per unit length. So how do we find the charge along this blue segment of the wire here of length L? Okay, we're going to use our relation up here for converting between charge density and the actual amount of charge in that length of the wire. So here we have a wire of length L and of density lambda 0. So the charge is going to be obtained by multiplying lambda 0 times L. Okay, perfect. And at this point, we've done the two simplifications that you'll need to do every time in Gauss's law. We simplified what is the area on the surface, and we simplified what's the charge enclosed within the surface. Okay, now all there is left to do is to divide stuff over. So, as I promised, the L's do cancel out just by dividing through. And if we divide both sides by 2 pi r, we get our answer immediately. Let's see, we're left with lambda 0 upstairs and 2 pi epsilon naught r downstairs. Awesome. And that's the answer for what the size of the electric field is off of a wire. And remember, this tells it to you at a general distance away, r. So not only does it tell you the electric field at this radius, it also tells you the electric field at some other radius if you just plug in a different number for r. Great. And just a reminder, it is generally expected that when you give this answer, you'll also tell your professor what direction the field is pointing. So if you also want to specify the direction of the E field, it points radially outwards again. Traditionally, since it's a cylinder, sometimes people use the symbol rho hat. Other people use r hat, and I think I'm going to stick with r hat, even though it has a different meaning in cylindrical looking systems versus spherical looking systems. But I think this is the preferred notation, but just be on watch for that. Great. All right, that's the second example done. Okay, now something else to know about Gauss's law is that there aren't really that many examples, and there also really aren't that many problems that you can even be given, because the tool is kind of too powerful for the cases that it covers. It gets too easy. So there's one more example I can think of. Well, I suppose technically there's two, but there's one more example that immediately comes to mind that you will likely, I could even guarantee that this will be a test question. Okay, I can almost guarantee at any place across the world that this will be a test question. It's going to be the case of not a point charge, but a spherical shell, not a shell, a spherical volume of charge. Okay, so it's sort of uniformly filled in with this charged substance. Okay, so I'm going to put this as a challenge example. By the end, once you've seen it a couple times and know how to do it, it will become just another thing that you know how to do. However, the first time, it will be difficult, so don't worry if you get disoriented. So I'll put in parentheses, will be difficult to understand first time. Okay, so the problem is going to be you have this spherical ball of radius A. Oops, I should probably write that outside. And the question is, what is electric field inside the ball? That's going to be sort of a separate question, as we'll see. And then what's the electric field outside the ball? Okay. And we're going to use Gauss's law because we have a nice symmetrical setup. Okay, so let's tackle the case of being outside the ball first. And I'll explain, there's not really a reason why you do that first. It just turns out it'll be easier. And then we'll tackle the more difficult case of inside the ball afterwards. Okay, so outside the ball, first let's sketch what we think the electric field looks like, just off of symmetry arguments. So we have this perfectly round ball. It really shouldn't depend on where we put the electric field test, here or here or here, because the ball looks the same from all of them. And it also shouldn't depend on anything except for, the electric field shouldn't point anywhere except for radially outwards. This looks almost exactly like a perfect point of charge, and there would be no reason for it to point this way because the charges here and here sort of cancel each other out. So we know that the electric field, roughly speaking, is going to point radially outwards, almost identical to a point charge case. Okay, so we've drawn our electric field sketches, and now let's draw a Gaussian surface. Okay, so Gaussian surface, we look at our field lines, we say, hey, a spherical shell looks pretty good, and that is going to be the right answer, right? Because the electric field lines are the same size everywhere on the sphere, and they do point perpendicular to it at all times. So the spherical shell is again the winner. And this is the same as the point charge case, by the way. Okay, we've picked our surface. Now we can just instantly write out Gauss's law. Now remember, since we've picked a nice Gaussian surface, we've picked really smartly, it just simplifies to electric field times the area of the surface is the enclosed charge divided by epsilon 0. And I should have told you guys the information of the problem is the charge density of the ball is rho 0, or rho naught. So again, I'm not giving you the total charge of the ball. I'm going to give you the charge density of the ball. You know what? At the end, sometimes problems will give you Q instead. And I may well choose to do an example like that at the end because this problem comes up so much. So I think I actually probably will do that at the end. But let's say I give you this for now. Okay, we're just going to do our turn the crank. There's two simplifications to make. What's the area of our Gaussian surface? Which I probably should have drawn in yellow here. Okay, what's the area of that spherical shell at general radius r? Well, the area of a sphere of radius r is just 4 pi r squared, just like for the point charge case. Okay, and the second thing we need to do is simplify the enclosed charge at this general radius r. Now, how much charge is enclosed? Well, no matter what radius we're at, the entire ball of charge is enclosed. So really, it's just a question of how much charge is there total on the ball. So the way you do that is, remember, if you're given a charge density, so coulombs per meter cubed, your job is to multiply by the volume of the object in meters cubed to get to the amount of charge. Right? So in our case, let's see, we have a density of rho 0, charge density, and we multiply by the volume of this sphere of radius A. Not radius R, but radius A. Okay, that's important. So the volume of a sphere is 4/3 pi times its radius cubed, but we're going to resist the temptation to write R cubed because the radius is A cubed. Okay, and at this point we've pretty much finished the problem. All we got to do is move 4 pi r squared to the other side and we're done. Okay, and if you want, you can cancel these and cancel the pi's and move the 3 down to the bottom. Perfect. And this is your answer. And one more time, if we wish to specify the direction as well, we can just write that it points radially outwards. Okay. Now let's tackle the case of being inside the sphere. And again, this is the challenge part. Do not fret if you don't get it the first time. It's all a matter of eventually getting what it's getting at and then being able to reproduce it for the most part. Okay, I'll redraw our setup here. Oops. We have this ball of charge, but this time we are inside of it. So we're going to draw what we think our electric field looks like on the inside. Okay, now there's a couple ways you can do this. Way one would be when you're inside a spherical charge distribution. The shells outside where you currently are, let's say you're currently at this point, the shells from here to here don't contribute to the electric field, so they don't contribute to its size, its direction, so you can basically ignore them when asking what's the electric field at this point right here. Okay, the other way is sort of just by symmetry arguments, but that's less, I guess it's more or less the same amount of intuitive. It's a perfect sphere. It would make no sense if something pointed like clockwise because it's symmetrical. It can't point one direction. There's nothing to make it choose one direction over the other. The only option you have is something pushing radially outwards. And again, the size of the arrows should be the same at a given distance away from the center. So we have a situation that looks almost identical to before, and indeed the correct choice is going to be that the Gaussian surface is, again, this spherical shell, but this time it's just inside. And again, it's at some generic radius r. And at this point, the diagram is getting really crowded, so sorry for that. And this is of radius a. Okay, so Gaussian surface is again a spherical shell. Oops. Okay, and now what we're going to do is write out Gauss's law because we've had our surface selected correctly. So we have E times the area at that r. We're at some radius r of our surface. Actually, I'll make this green just for keeping track. And that equals the enclosed charge at that r, and this is going to be the tricky part, divided by epsilon naught. All right, as usual, we have two things to simplify. The first is going to be the area at that r of this Gaussian surface in green that we drew, which is just, as usual, 4 pi times r squared. Okay, it equals the enclosed charge over epsilon naught. Now, the question is, what is Q enclosed now as a function of r? The enclosed charge is going to grow as we expand our circle out. Will grow as r is made bigger. And this is how it differs from the previous example. So what's the Q enclosed as a function of r? Well, just as usual, it's the density of the ball times the volume of the ball. Okay, and the volume of the ball is 4/3 pi r cubed. So again, here we see a reflection of this fact. The enclosed charge, this thing that's circled here, it increases as we make our Gaussian surface bigger and bigger, which is something we haven't seen before. However, that really is all there is to it. Now that we've filled in this step, and this is the conceptually difficult one, that the enclosed charge might not be the same number as you grow this green surface outwards. But as soon as you put that in, you're back to the grind. All you have to do is divide both sides by 4 pi r squared now. And you'll get your final answer. Of course, there's going to be a little bit of simplifying here. Okay, let's see, the pi's cancel, the 4's cancel, and here's the interesting part. You have 3 factors of r upstairs and 2 factors of r downstairs. They cancel to leave 1 factor of r upstairs. And this is your answer. Now, this is super unusual. The electric field grows as you go outwards. Okay, this is unusual but correct. Now, why is this? Right? We're always used to seeing things fall off as you get further away from the source charge. The reason is that, remember how I said these shells out here don't contribute? And by the way, this isn't the most important thing. It's just an explanation for why it's okay that the electric field gets stronger as we get further from the center. Shells outside of where you are don't contribute to pushes of the electric field. So when your radius is really small, I'll do it in red. When your radius is really small near the center of the object, you don't really have a lot of shells pushing you outwards. As you get further out to bigger radiuses, all these shells in here are now able to push you outwards. So the amount of total push you get is getting stronger until you hit here, right? Until you hit r equals a. At that point, you're outside the surface, and as you get further away, you don't have more shells pushing on you. So once you reach here, so once your radius reaches here, the E field will start falling off again. Like you're used to. Okay, perfect. And one more time, if you want to specify the direction, you can put an r hat on there. Now, one final comment before I wrap up this video. I might choose to tack on more examples or maybe do them in a later video because they're really important to cover. One final note is that each of these cases, so we have one answer for inside the sphere, one answer for outside the sphere. The remark is that each expression is only valid in a specific radius range. So the first one is only valid when radius is greater than, I think, or equal to. I think the electric field should agree at the surface. It's only valid when r is greater than or equals to a, this one. So rho a cubed over 3 epsilon naught r squared. Okay, and this expression that we just derived, it only works when r is between 0 and a. Right, because as soon as we go to Gaussian surfaces bigger than a, this expression for the volume stops working because we stop tacking on things with charge densities once we go outside that radius. So we had to consider the two cases separately and divide them artificially at this boundary. Okay, so this would be a full 100% test question and answer. And again, this problem appears all the time on tests. Now again, it is challenging the first time. So if you didn't get it, don't worry 100% yet. Go back, rewatch the video. Maybe when it pops up in your homework, you'll be able to figure it out with this sort of guidance, knowing that there's like a special second case where your radius is less than a. And before you know it, this will become really second nature. All right, guys, I'm going to wrap up the video there. Like I said, I might end up putting out more examples, perhaps for a fat wire carrying a density. It'll be very similar to this last example, but I'll put that out in a later video. All right, good job today, guys. Gauss's law covered, and I will see you in the next one.